Hello and welcome to this video. This is a re-recording of the GPT-3 paper presentation that I gave at the Hasso-Plattner-Institute in Potsdam. In previous session of the paper reading group, we already covered some papers that are maybe important to understand the GPT-3 paper in depth. So to fully understand the concept in this talk, you should be quite familiar with the Attention is All You Need paper and also the BERT paper, or have at least watched some videos of those two. Otherwise, I hope you can still find some value in this presentation. I really want to re-record this video to share the knowledge and make it available to people that aren't as fortunate as me to be in this specific working group. So yeah, welcome to the presentation of the GPT-3 paper called Language Models Are Few-Shot Learners. It's quite a long paper actually. It has 75 pages, but also it's a super interesting one with all the hype that was created around it last year. As probably a lot of you know, the model became quite famous in the summer of 2020 for performing various NLP tasks like language, like text summarization, question answering, but also stuff like code generation without any supervised learning that was necessary. So let's kick it off maybe with the hype that was created around this to get us all motivated to learn more about the paper. A lot of you have probably seen those videos that popped up in the summer of last year where GPT-3 can write apps. Here, for example, can create a natural language via natural language description, the website, the Google website, or GPT-3 can write React apps, all this kind of stuff. And also a bunch of mainstream media was talking about GPT-3, which usually doesn't happen when a new language model is released, that the New York Times is writing about it. So there was definitely some hype around it, and also some fear that this could be like the super intelligent AI that a lot of smart people were talking about. And today we will see, is that really the case? Is it that smart, or is it mainly hype? So what was the motivation in general of OpenAI to create GPT-3? The BERT model from Google, for example, or other models need task-specific fine-tuning datasets of thousands of examples to be used on a specific task. And there are some reasons that are against those large data sets that you need for fine-tuning. First of all, it limits the applicability of the new tasks. So it's always difficult to always create or find new data sets. And another reason is that humans do not require those large supervised data sets to learn most of the tasks. So for us, most of the time it's enough if we get some few examples or even sometimes a description of a task enough so we can perform it. So the idea was basically to scale up those language models that they had to improve the task agnostic performance. So that stuff like you have to do with BERT fine-tuning on thousands of examples isn't necessary anymore. And there was already a trend that was going into this direction. We already could see that, for example, BERT Large had 340 million parameter models, and GPT-2, the previous version from GPT-3 that we will briefly talk about too, had already 1.5 billion parameters. The second largest one before GPT-3 had 17 billion parameters called Turing NLG from Microsoft, and GPT-3 scales it up rapidly. It has 175 billion parameters, so even 10 times more than the second biggest one. And one of the major difference now between, for example, BERT and GPT-3 that I already mentioned in the motivation is that GPT-3 doesn't need a large supervised data set to fine-tune it for a specific task. GPT-3 works with something called in-context learning, where the model is conditioned on a natural language instruction or description, and sometimes a few demonstration of a task. And then the model is expected to complete further instances of the task simply by predicting what comes next. And this can be done in different fashions. This can be done in, for example, the zero, the one shot, and the few shot setting. And for the zero shot one, there are no examples necessary. So you just give the task description to the model, for example, here, translate English to French, and then you put the prompt into the input called cheese, so it has to translate cheese. In the one-shot setting, the model gets at least one example, and the few-shot setting, the model gets a few examples, basically 10 to 100, depends on how many you can fit into the context window of the model, which is 2048 tokens. We will talk about that in a second. And in comparison, we see the fine-tuning approach on the right side that a model like BERT, for example, uses. And there we can put in examples into the model in like batches. And once the model went through one batch, it does a gradient update, it updates the weight of the model. And that's especially important in comparison to the GPT-3 model. Even if we put some examples into the few-shot setting here, it doesn't update the weights of the model through that. It just filters for examples, or it uses those filters for reasoning. So how does a specific model architecture from GPT-3 look like? To be honest, that wasn't too easy to find out. The GPT-3 paper just said we use the same model and architecture as GPT-2. GPT-2 paper said the model largely follows the details of the OpenAI GPT-1 paper. And the GPT-1 paper finally had some nice diagrams that I could use for this presentation. And also another fun fact that I found out is that apparently OpenAI doesn't only scale up the language models from version to version, but also the paper length. We could see that GPT-1 was 12 pages, 170 million parameters. GPT-2 had 24 pages and 1.5 billion parameters, and GPT-3 75 and 175 billion parameters. So I'm curious how many pages the GPT-4 paper will have. So I'll plot this on the right side here. So, but let's get really into it. How does the GPT-3 model architecture look like? And if you already read the BERT paper or read about it for a while and you're familiar with the transformer, this isn't too difficult to understand. So basically the BERT paper only uses the encoder part of the transformer architecture, this one, and the GPT-1, 2, and 3 use the decoder part, a modified decoder part that we will talk about in a sec, of the transformer. The model is trained, the OpenAI trained 8 different model sizes of GPT-3. The smallest one has 125 million parameters, the biggest one has 175 billion parameters. And as you can, and the largest one is also the one I will be referring to during this presentation mainly when I talk about GPT-3. So GPT-3 has 96 stacked attention layers. So 96 attention layers on top of each other. In comparison, for example, BERT Large has 24 stacked attention layers. It has 128 attention head rate, can focus on 3.2 million is a batch size, which is super large, and has a relatively low learning rate, since apparently larger models require a smaller learning rate. And the context size of the model is 2048 tokens. I don't think it says it here, but I have it in my notes. So yeah, this is a nice visualization I found online of those 96 attention layers where you put in the words and it runs through those stacks transformer decoders. And what's also important to mention is that GPT-1, 2, and 3 are autoregressive models. This means basically that during pre-training, it just sees the content from left to right. So it only does pre-training on the following task, which is next word prediction, where it has the knowledge of all the previous inputs, but not of the future inputs. It just does next word prediction. And this is in comparison, for example, to the BERT model. If you read that paper, you can see that this model is trained on pre-training tasks which are bidirectional, where word gets context from both sides, basically. And we will see that this autoregressiveness from the GPT-1, 2, and 3 models, that's a trade-off, basically, that they are autoregressive and unidirectional. Because it also says in the BERT paper that this bidirectionality gives it way more, way better performance on specific tasks. And we will also see that the results later that on some tasks GPT-3 isn't performing that well because probably it doesn't have this bidirectionality. Next up, I want to talk about the GPT-1 architecture to go from GPT-1 to 3. So first of all, as I already said, it's based on this modified decoder. We can see that each block of those in the transformer, each decoder block contains of a masked multi-head self-attention, layer normalization, and then a feed-forward network. It has a loss function of a negative log likelihood, and the input sequence is encoded via byte pair encoding. So I want to briefly talk about byte pair encoding, not go into too much detail. I think there are better resources than mine here to learn about that. But it's basically instead of just putting white space separated words in as a sequence into the model, you can encode them before via byte pair encoding. So this is basically an algorithm where you can split up words in sequences into subwords. Basically, you can split up words into subwords with character combinations that appear most often. So you would probably do a subword with EST because in this sequence it appears more often. So it's basically a simple algorithm that you can use for that, and it creates a balance that you don't put characters into the model, but also not words representations. This has some benefits that you can, for example, encode any rare words in a vocabulary, and you don't have unknowns. If you have a super long word that the model has never seen, you won't have an unknown because it can split up it into subwords. And as you can see already, I don't want to go into too detail in this one because we are mainly interested in the GPT-3 model and how it does things. But in the paper, they already showed that it already got somehow rid of this task-specific modeling in the GPT-1 paper and uses those pre-trained language models directly if you form your input sentence in a specific way for a classification task, for example, or for multiple choice parts. Next up, we have the GPT-2. Next up, we have the GPT-2 architecture, and we will look at the model differences in the architecture to GPT-1. So what is the main difference here is that the layer normalization was basically moved in front of the masked multi-self-attention. It was previously after the masked multi-head self-attention. And also we got an additional layer normalization after the final self-attention block. Another small difference is that it uses still byte pair encoding, but this time with UTF-8 byte sequences, which basically supports more characters and has some other nice performance features like that specific characters aren't getting merged anymore. And GPT-2 was already evaluated in the zero-shot transfer setting. Not in the few-shot transfer setting, as we will see in GPT-3 or already saw, but in the zero-shot one, where you, for example, you put in for machine translation, you put as an input into the model that it has to translate English to French, and then the prompt it has to translate cheese. Or for summarization, you put the article as an input, and then you put too long didn't read, and it has to summarize the article. And it was already performing okay on those zero-shot tasks. But for a lot of tasks, you still had to fine-tune GPT-2 with a supervised data set to good performances. That's not the case with GPT-3. It got out of the box just with the pre-trained model, quite good performances. And also it isn't even possible right now to fine-tune GPT-3 because OpenAI doesn't allow it with their current API access. Next up, we have the GPT-3 architecture. So the model data and training is super similar to the GPT-2 model, just with a scaled up model size, dataset size, and length of training. So it has the same model and architecture as GPT-2. The only difference they make, and that's the only sentence they say to it in the paper, it has alternating dense and locally banded sparse attention patterns in the layer of the transformer, similar to the sparse transformer. And this obviously raises the question, what is a sparse transformer? And they didn't explain that at all in the paper, so I will try to do that now. So for a normal attention mechanism, every input element or every output element is connected to every input element. And this requires the creation of an n times n matrix for every layer and every attention head. And this basically creates or consumes a large amount of memory. So they got this idea of sparse attention patterns, where each output position only computes weightings from a subset of input position, not of all input position. And why is that even possible? Why don't you need all the positions? So this is possible because some attention layers show some structured sparsity patterns. And this can be best visualized in a transformer for image data, basically, as you can see here. And we can see the pixels on the screen highlighted in red here. Those are the focus of the attention heads when predicting the next value, basically. So the white stripe here, or the white dots here, are the attention patterns. And in layer 19, as we can see here, this is an example layer for a layer where we can see those sparsity patterns. If we predict the next pixel or the next value here, the attention heads are only focused on this row, nowhere else. In comparison, we have the layer 36 over here, which shows that some layers have some dynamic attention that stretch over the entirety of the image. When you want to predict the next value, there are white dots all over the image, so the attention is all over the image. But what they basically found out is that a lot of layers look like the one on the left, where they have those sparse structure. And the conclusion from this was that some form of sparsity can be introduced to the attention computation without significantly affecting the performance. So they introduced those sparsity. So they introduce sparsity inside those attention matrices, and how they do it is by the factorization by those two-dimensional connectivity subnets that you can see here. And I don't want to go into too detail on this calculation that is happening here, but what it's important to know is this basically reduces the computation time and the memory consumption of transformers. And in the end, this is even what it makes it possible that you can build attention networks or train attention networks with hundreds of layers and on very long sequences. Next up, I want to talk about the training data that was used for training or pre-training GPT-3. And first of all, they used Common Core, which is basically a crawl of the entire internet. And this crawl would basically be big enough to train even their biggest model without seeing any data twice. The issue with Common Core is, though, that it has quite a low quality of the data. So they filtered Common Core for quality documents and also for deduplication, so they don't have the same data in their training and test set in the end. And also they added some other data sets for better quality. So they added the web text 2 one, which is also a web scraper, but with higher document quality. For example, they only scraped the outbound links from Reddit, where the post had more than 3 comma points. Also 2 books corpus and the English language Wikipedia. And what's also important to mention is that they showed the better quality data more often to the model than the lower quality data. So as we can see here, Common Core, which has quite a low quality, was only shown to the model 1.44 times. So not even the whole data set was shown to the model once. And for Wikipedia, which is quite a high quality, the model saw it a few times, 3.4 times. So let's talk quickly about some training details from GPT-3. So they used those V100 GPUs that were provided by Microsoft. And obviously they had to use model parallelization because otherwise they will run out of memory very quickly. And the specific costs for training GPT-3 weren't mentioned in the paper, but some people guessed it based on the computation numbers they had in the paper and came up with $4.6 million as a cost if you would run it on the cheapest V100 GPU that was available by some cloud provider for the next 355 years. And I added a link for the specific calculation if somebody is interested in that. And also another interesting fact is that they had a bug in filtering out the overlaps in the train and test set, but they couldn't retrain the model because it would have been too expensive to retrain it. And this just shows how expensive like bugs in language models will get in the future. And in the future, while building those language models, we should maybe think more of building something like a Mars rover, which better doesn't have any bugs because otherwise it will be quite expensive. Next up, I want to talk about the results from GPT-3, which were quite impressive. And also the length of the results section was super long but also super interesting. And yeah, GPT-3 was trained on or tested on several tasks. And yeah, for like traditional language modeling tasks like Lambada, question answering, translation, vinaigrette, common sense, reading, superglue, and NLI. And also some additional tasks that were specifically designed for GPT-3 to test how it can do reasoning and is novel in their answers. And yeah, I will talk briefly about all of them. I will start with the ones where GPT-3 is performing the best to maybe see the differences. Why is it performing so good on Lambda and so bad on those at the bottom here? So let's get into it. So Lambda is a dataset that tests a long-range dependency in text via a next word prediction task. And it's super impressive to see the results from GPT-3 here. The previous state-of-the-art was 68% on Lambda, and GPT-3 increased that by over 18%. So why is that? I looked at an example from this Lambda dataset, as you can see here, and it's basically perfect dataset for GPT-3 since if you look at the example, it's basically a next word prediction. You have to predict the last word in the sentence here. And that's exactly what GPT-3 got pre-trained on. So the high score isn't that surprising for me. Next up, we have question answering tasks, and they tested it on 3 open domain QA tasks. And one way it's super impressive what GPT-3 does is trivia QA. As we can see, the previous state-of-the-art in trivia QA was WEC, which is a fine-tuned open domain model. So basically it's fine-tuned, it's only trained for this task in particular, and it's also open domain, which means it can go and look at Wikipedia, look at a Wikipedia page and find the answer to the question. And GPT-3 is still better than this fine-tuned model. And another thing is also that the bottom graphic here shows that all the zero, the one shot, and the few shot approaches, all the performance grow with the model size if it increases. And this basically shows that larger models can absorb also more knowledge. Next up, we have translation tasks. This one is also super interesting since GPT-3 got trained only on 93% on English data, basically, and 7% in other languages, and it still performs quite well on translation tasks. We can see it here. GPT-3 outperforms or is super close to the state-of-the-art when it translates into English. So from French to English, it outperforms the supervised state-of-the-art. From German to English as well, and from Romanian to English, it's super close to the state-of-the-art. And this just shows the strength of it as an English language model. And it's also super fascinating since I don't think GPT-3 was ever especially made for translation. In the training data, they even excluded all the other Wikipedia sites. They only use the English language Wikipedia, not the other ones like the German one, for example. And another interesting thing is to see is that GPT-3 is close to the unsupervised state-of-the-art, at least when translating from English to another language. So from English to French, it's close to the unsupervised state-of-the-art, quite close. From English to German, it is super close to the unsupervised state-of-the-art, and here it's still pretty far away. Next up, we have vinaigrette style tasks. Those tasks are about determining which word a pronoun refers to. And we can look at an example here. The city councilman refused the demonstrators a permit because they feared violence. And what the model has to do is to say if does they refer to the city councilmen or the demonstrators. And for us humans, it's quite intuitive that it refers to the city councilman, but for language models, this isn't that intuitive. It has to understand long-range dependencies, basically. And as you can see, GPT-3 is as good as a fine-tuned Rebeta large model in the few-shot setting. It's still a few points away from the fine-tuned state-of-the-art and pretty far away from human performance. Next up, we have common sense reasoning task, and they tested it on 3 common sense reasoning datasets. First one is physical QA, next one is ARC and OpenBook QA. Physical QA is one where the model is asked a question about how the physical world works, and it achieves a new state-of-the-art here. ARC is a dataset where it gets multiple choice question collected from 3rd to 9th grade science exam, and we have OpenBook QA. And on both of those, the performance from GPT-3 is much worse than the state-of-the-art. And what's also quite interesting to see is that on this physical QA task, it has such a good performance, and the other one it doesn't. And they also mark it with a little star here, which says that the data is contaminated, which means that there was a significant overlap in the test and in the training data of GPT-3 and this physical QA data set. So they said basically that this shouldn't affect the performance too much, but I pretty much doubt that, because those 3 tasks are so similar and the performance is so different. It's the state of the art here, and here is it's so far away from the previous state of the art. So you can think for yourself, but I doubt that it would perform so good on physical QA when there wouldn't be the data contamination. Next up, we have reading comprehension. That was tested on 5 datasets, and the performance varies a lot between those datasets. But you can see that GPT-3 is basically nowhere the state of the art. And it's especially weak on the Quark, on the Squad, and on the Race dataset. And I read a lot of comments online that this could be caused by the unidirectionality of GPT-3. As we already said in the model architecture part, that models such as BERT are bidirectional. So it could be beneficial for those tasks like reading comprehension to have the context from both sides and not only read it from left to right. So that's why it maybe performs so bad on those data sets. Next on is the superglue benchmark, which is a standardized collection of data sets where it gets 8 different tasks basically. And the main result from this benchmark testing is that GPT-3 is quite weak at tasks that involves comparing 2 sentences. And you can see that in the WIC accuracy here, in the RTE one, and also in the CB one, which involves such tasks. Such, for example, is a word used in the same way in 2 sentences. And also it has a quite low performance on BullQ. And let's take a look at an example here to maybe understand why that could be the case. So you get a question and a passage for BullQ. The question is France the same time zone as the UK? And a long passage that I cut off here. And the model basically has to do reasoning based on this passage to answer the question. And because it has a lot of reasoning, GPT-3 is apparently not that good in those tasks. On the other side, GPT-3 is close to the state of the art on the COPA data set here. And we can look at an example for COPA here. So you give the premise as context to the model, and you have an alternative 1 and an alternative 2 where the model has to decide which one is more likely to come. So the premise in this one is the man broke his toe. What was the cause of this? The alternative 1 is he got a hole in his sock, or alternative 2, he dropped a hammer in his food. And for the model, those tasks are easier because the model will probably select the things that happened more often in the training data. So basically, broke his toe and hammer in his food is more often together in the training data than broke his toe and hole in his sock, which doesn't make any sense, right? So it's basically less reasoning necessary to answer those tasks. Next up, and the last evaluation before the additional task that I want to talk about is the natural language inference task. They tested it on the adversarial natural language inference data set, which tests the ability of a model can understand if one sentence apply another sentence. And the test and the ANLI has 3 rounds, and we can see the result for the third one here on the right. And we can see that GPT-3 is only slightly better than random. So it has a super low performance on this task. And yeah. Next up, we get to the tasks that they tested it on that were especially designed for GPT-3, where the model has to find novel patterns that are unlikely to have occurred in the training data. And one task here focuses on arithmetic. So basically, no one teach the model or taught the model how to do arithmetic. And if the model can do arithmetic, the model must have learned it on its own to do it. And we can see that the model can do arithmetic basically. For the 2-digit addition, it has an accuracy of 100%, and the performance decreases as the number of digits in the calculation increases. So for the 3-digit addition, it only has an 80% chance. And for the other ones, like 5-digit, I think it's over here at like 15%. And why could that be the case that it is so good on those smaller digit calculations than on the other ones? One reason could be that it just memorizes the calculation so that the 2-digit addition is always inside the training data. But what they did was that they checked if the additions are in the model data, in the training data. And for example, for the 3-digit addition, they only found a match of 0.8% in the training data. So the model must have learned how to do arithmetic and can't just memorize those strings. But I also saw a lot of comments online that didn't agree too much with the conclusion the authors made from this result. So what they basically said is they didn't search well enough in the training data to find this. For example, one comment from Yannick Kirchner was that it could also learn that from tables, basically, where you have one column here, which has this 19, another column here, 23, and a bunch of other numbers. And the third row is always the sum of the first 2 columns. So here it would be 42. And it could learn it from those tables, which they didn't look for in their training data. But it's obvious that those bigger numbers can't be all in the training data. It must do some reasoning here. And also we will look at this one now. So this is the update that OpenAI gave at NIP's presentation for the GPT-3 paper, where the interesting thing that they noticed was that if you insert a comma for the 4 to 6-digit addition, the performance became way better. For the 4-digit addition, it went from 25% to over 90. So if you just added 23,000 comma 376 instead of just this. So this shows the fragility of GPT-3 that is so sensitive basically to those little changes. And also a nice little comment from Andrew Campari from online, where he said that prompt development will be maybe a real thing in the future, so that you have to design the prompt that the model can understand it. Next up, we have SAT analogies. This is a data set where the model is asked some multiple choice question of a section of the SAT college entrance exam that every student in the US has to do if they want to go to college. And the funny thing to see is that GPT-3 outperformed the average college applicant, which is at 57%. And I don't know why they didn't include that in the initial drawing here, because I think that's pretty funny that GPT-3 is stronger than the average college applicant. And the last evaluation that I want to talk about is news article generation. So they tested something with humans. So if they could differentiate GPT-3 generated articles from real articles, and for the largest model, the 175 billion GPT-3 model, the humans could only differentiate GPT-3 generated articles from real articles with an accuracy of 52%, which is crazy because it's only slightly better than if you would just guess, which would be 50%. And a lot of people were freaking out because of those results, that this would replace writers because GPT-3 can write as good articles as we could. And you could see us at that. You could see that the model learns the language so well, it keeps context, it does reasoning. Or on the other side, you can conclude that the model just sees the title here, it sees the subtitle, and it sees maybe some few short examples for the first sentences in the article here. And then the model just filters out their training data for those inputs and outputs the training data in a slightly different way. The counter argument from OpenAI, though, is that they check those results, and those news articles are not on the training data, basically. But a lot of people check that too, and a lot of results basically wouldn't withstand a plagiarism checker. So I wouldn't use this article generation for writing my master thesis yet, but maybe sometimes in the future. And also this results in particular should create some awareness that for the potential misuse of those language models that are possible. At the end, I want to talk a bit about the limitations and the possible future developments for GPT-3. So as we already said a few times in this talk now, GPT-3 has some structure and algorithmic limitations. For example, it's a unidirectional model, so making it bidirectional would maybe improve the performance on such a lot of tasks. So GPT-3 is basically based on a architecture that's outdated. That is from early 2018 when they released GPT-1. So improving the model architecture could maybe help. Another interesting thing is this diagram, as you can see here. It raises the question basically if we could scale the model even further. So as you can see here with the GPT-3 one, and when they stop, basically, it doesn't look like it stops here. You could maybe go even further and create a model that has even lower loss. So there's the scaling hypothesis where Gran already had a nice blog post about too. So that we can maybe, if we put more than $5 million into it and put $1 billion or more than that, which wouldn't be a problem for a lot of like big players like Google or even nation states, that we could create an even way better GPT-3. And the last point I want to talk about here is the sample efficiency from GPT-3. So this one is still quite poor. So it already was in the right direction. It already goes in the right direction with GPT-3, where you have one-shot learning and few-shot learning approach now. But a human has to see way less data in the lifetime than GPT-3 does during pre-training. So I personally, and you probably didn't see the whole internet such as GPT-3 did, but I think I personally can still perform a lot of tasks better than GPT-3 does. So that's some point to improve for the future. Here I just noted down like two simple points for the main contributions for the paper. You could make that even longer probably. So featured learning is one of the main contribution was that featured learning achieves competitive or even surpasses state-of-the-art models that wasn't even close before. So the realization of what you can do with featured learning is there now. And also GPT-3 shows a language model to perform better as they scale in size of model data sets and computation. Next up, I want to show a quick demo of GPT-3 because I finally got access to the GPT-3 API. So as some of you may know, the GPT-3 access was the access strategy where only a few people and selected partners got access to it in the summer of 2020. But now they apparently opened it a bit more since I got access. And yeah, I would just show some quick examples now. So this is the playground that OpenAI provides for interacting with the API in an easy way. I actually didn't play around with the API in general yet. I just tried out those examples here. But as you can see here, we would try the chat example for now. So you can put a task description into the model. So the following is a conversation with an AI assistant. The AI assistant is helpful, creative, clever, in a friendly way. And you can put in some few-shot examples basically here. And let's try to change the task description. We could say the AI assistant is Elon Musk that wants to talk about rockets. I want to talk about rockets. And how can I help you today? What do you want to talk about? That should be pretty simple for GPT-3. What do you think about rockets? I like them. What about you? I think rockets are quite useful. I prefer discussing about them more than other things. That's a pretty boring answer. Why? Rockets would have common topics. It's pretty generic answers and not that interesting. Maybe we should try something else in the chat one. We could try the Q&A one. Let's see how smart GPT-3 actually is. Oop, I'll correct myself there. So you put the task description that you want to do, like Q&A task basically now. You could put some few-shot examples. And we will ask GPT-3 if is Germany bigger than the US? Yes, Germany is bigger than the United States. I would pretty much doubt that. I'm pretty sure the country I live in is pretty small compared to the US. So we saw that GPT-3 doesn't have all the answers yet, but it's still super smart, and it's a lot of fun to play around with all those examples here. Let's get back to the presentation. So that's basically it for the presentation of the GPT-3 paper. I added some additional readings and references over here that you should maybe check out, especially the grain scaling hypothesis blog post is super interesting, but also a few other ones if you want to see some other visualization of GPT-3. And also as a last question, maybe for you guys, is the hype justified that is there around GPT-3? I mean, even Sam Altman, the CEO of OpenAI, says the GPT-3 hype was way too much in the summer of 2020. And yeah, just want to see what other people think. And yeah, thanks for the presentation. Please let me know how I made this presentation. I didn't get too much feedback for it yet, but would be curious to hear. Peace.